Okay, welcome to all of you. I see that we have 25 people in the class at start, and usually it grows up to a little bit more by the time we finish. So today we are going to continue with what we started last Saturday, and that was the 2019 Junior Round 3 SAMO paper. We finished 2018, the 15 problems there, and we also did 5 problems from 2019. And today we are going to try to finish the remaining 10 problems. And I don't think we're going to go much beyond 10 problems, 2019. I don't think we'll go into 2020 because I've got a lot of some nice facts to tell you. I'm going to do a little bit of teaching today. So you will learn a few techniques and few ideas along with the lessons. All right, so let's go straight to the problems under investigation. All right, so the first problem is problem number 5, or problem number 6. We have finished 5. And this is this problem. It says, draw a loop through some points on the grid such that there are various conditions. Now, a loop means you start and end at the same point. It's a full circle, right? Not a full circle, but a full path. So you're going to go along these lines here, the horizontal and the vertical, in any direction. And you mustn't cross itself. If the loop has gone here, you can't go across it. That's the first one. Let me just get the pointer. It goes through all black and green circles. Okay, there's only one black circle, and this loop must cover the whole lot. And secondly, it turns in a black circle. So at the black circle, it will turn. I think that is kind of obvious. And continues straight for at least one segment before and after the turn. And it passes through every green circle. Now, what this actually means, and I don't know whether they are saying this in clearly, see, once it turns, if you make a turn, like for instance, you went up here and you turn here. Now, before you actually take the turn, you must go through 2 segments at least. Okay, one full segment. So it means that you have to go through, there should be 2 dots before you turn. Like for instance, if you come down here, so if you come down here, and if you turn, that's fine because there were 2 dots before the turn. But when you go here now, you can't turn again. You can't turn here because there is no dot. You'll have to go right through. So before and after, you need to have at least 2 dots. All right, so those are the rules. I'm not going to do this. You can try this thing, various strategies, and see whether you can satisfy the conditions. But if you are going straight, you can go through two circles without any. For instance, you can go right through here. Right? These rules only apply at a turn. Right? Okay, so it's at least one segment before and after the turn. All right, so I'm not going to do that. This is a something that you have to try on your own. Let's get on to the next question. This is question 7. The question says, let n be the smallest multiple of 84, which consists of only the digits 6 and 7. Right? Show that n ends in 76. There are 3 parts to it. Prove that the number of 7s in n is divisible by 3. So in other words, number of 7 in that number must be either 3 or 6 or 9, the number of 7s in your number. So you have to prove it. And then they say find n. N, remember, is the smallest multiple of 84, which consists, and its digits are only 6 and 7. Okay, so those people who came in late, we are now tackling number 7, question 7. And I'm going to use the whiteboard for this purpose. All right, so what do we have? We have that firstly, that the number n (84) is a factor of n. The way we write factors is 84, and you put a vertical line like that. That's a way of saying that 84 is a factor of n, which is the same as saying that n is a multiple of 84. Same thing. Okay, so it means that 7, this is 7 times 84 is 4 times 3 times 7, 12 times 7, and 12 is 4 times 3. So 4 is a factor of n, 3 is a factor of n, and 7 is a factor of n. Because if 84 is a factor of n, then all of these are also factors of n, because 84 is equal to that. So you have that. In particular, the first question says that this number ends in 76. So that's the question. Prove that the number ends in 76. Okay, so the question asks about the last 2 digits. And you know, when you do divisibility rules, the last 2 digits play a role when you talk about divisibility by 4. So let's start there. We know that 4 is a factor of n, right? Okay, because 84 is a factor of n. And so now that's the divisibility rule says, by rules of divisibility, now I want you to, there's a whole section on this in my book. I don't know what the reference is. See the book. I've got, in that book, I've got various rules for divisibility. Rules for divisibility by, rules for 3 or 2, obviously, a number is divisible by 2 provided the last number is even, you know that, which is the same as saying that the last digit is a multiple of 2. Rule for divisibility by 3. Okay, what is the rule for divisibility by 3? It is that the sum of the digits must be a multiple of 3. So 3 goes exactly into a number. If when you add up all the digits, 3 is a factor of that. So that's the rule for divisibility by 3. And then the 4 is when the last 2 digits is a multiple of 4. The 2-digit number at the end of your number must be a multiple of 4. All right, so the number could end in 04 or 08, or any multiple of 4, 32, and so on. This is divisibility by 4. And then we also have 5 is easy, it's either ends in 0 or 5. 6, it must be divisible by 2 and 3. 7, there's no rule. There are rules, but they are too complicated, so that we don't bother too much about it. 8, there is a rule. You can check that out. 9, there is a rule. 10, of course, there's a rule. And 11, there's a rule. And 12, there's a rule. So in each of these, there are rules. We stop there. Rules for divisibility by this. And we discuss all these in the book. Okay, so you can go and check that. Okay, so in particular now, you want the last 2 digits to end in a multiple of 4. Now you've got only 6s and 7s. The last 2 digits can end in 67, 66. Let's put it this way. The last 2 digits can be, okay, you can have only 6s and 7s. So you could have 66, 76, 67, or 77. Right? You only got 6s and 7s. And none of these is a multiple of 4 except 76. The 2 of them are odd. And this one here, it leaves a remainder of 2 when you divide by 4. 64 plus 2. So only 76 is a multiple of 4. So therefore, those must be the last 2 digits. So that's the first question. The second question is, right, the number of 7s is a multiple of 3. Forgive this bad writing because I'm writing, in a very unusual way. So this is the question. The number of 7s is a multiple of 3. Okay, now how do you prove this? You have to prove this. Okay, the number consists of only 7s and 6s. So let's suppose now this is a proof. Suppose there are x 6s and y 7s. It consists only of 6s and 7s. So if you want to check to see whether it is a multiple of 3, you add all the digits. Then the sum of the digits of n has got x 6s and y 7s is, if you add up all the 6s, you're going to get 6x. And if you add up all the 7s or y of them, you get 7y. Right? And this is a multiple of 3. So this is equal to, if it's a multiple of 3, no, I'm sorry. It is a multiple of 3 because n is a multiple of 3. Let me put it, is a multiple of 3. Because n is a multiple of 3. So the sum of the digits is this. So therefore, this is equal to 3 times something else. So multiple of 3. That's how you write a multiple of 3, 3 times something. And in this case here, you got x, y, and z are all natural numbers. Right? Or all positive integers. They're not, like half and 3/4 and so on. Because 3 times a whole number. All right, now, so what does this mean? It means now that 7y, if I make 7y the subject, 7y is equal to 3 into z minus 2x. See? So 7 times y is 3 times something, and 3 times anything is a multiple of 3. So 7y is a multiple of 3. I'm writing out everything in detail because you are expected to write these things out in detail. Now, for 7y to be a multiple of 3, this can only happen if y is a multiple of 3. You see, if you have 7 times 2, that's not a multiple of 3. 7 times 3, yes. 7 times 4 is 28. 7 times 5 is 35. 7 times 6, yes. You see, the reason is that 7 is not a multiple of 3. 7 and 3 have got no common factors. So if this is going to be a multiple of 3, that number there must be a multiple of 3. So therefore, y is a multiple of 3. And we said that there are y 7s. So what we have shown is that the number of 7s, that's y, is a multiple of 3. And that's exactly what we needed to show. We're making heavy weather out of this, but it's kind of common sense. In your mind's eye, if you're thinking of a number, visualize it. You're thinking of some number with only 6s and 7s in it. And then you're saying yourself, well, if I add up all these, is it a multiple of 3? Well, 6 is already a multiple of 3, right? So we can ignore all the 6s if you want to work out if this is a multiple of 3. So you're only adding 7s. So then you say, in your mind's eye, you say, I'm adding many 7s and it's a multiple of 3, right? And the only way that can happen is that the number of 7s itself is a multiple of 3. If I have 1 7 or 2 7s, it doesn't work. 3, it works. 4 7s and 5 7s doesn't work. 6, it works. So the number of 7s is a multiple of 3. So we could have, mentally, you could have figured this thing out. And then when you write it out like this, then it becomes a proof. And explaining everything nicely. Okay, and the last part is find n. Now remember, n is the smallest. It's the smallest number which satisfies all those properties. It's got only 6s and 7s. All right, now to find n now, we already know something about this thing. We know that it ends in 76. All right. Now we want the smallest possible n. So we say, okay, now suppose, and we know that we need to have 3 7s. You see, that's another useful thing. So I can put 7, 6. Now I could I want to have 3 7s. So let's try to put all 3 7s at one time. Try that. Right? That should be the smallest. Right? Is this the number that we've got? Well, certainly, you see, it needs to be a multiple of 7 as well. Remember, we eliminated 4 by sending it, say that it finishes off in 76. 4 times 3. We finished with 3 as well, right? That allowed us to get number of 7s is a multiple of 3. So the only outstanding one that we haven't used is 7. And this is not a multiple of 7. Because 7 does not go exactly, you can see quickly that 7 does not go into this. Okay, now we're looking for the smallest possible number. So let's try 7, 7. Maybe we can try 7, 6. We can't put 7, 7. So let's put a 6 here, make it 6. That. Now, but you need 3 7s. So you can try that. Or you can try 6, 7, 7. You got a 6 here and a 7 there. Like that. You need to have 3 7s, right? Ends in 76. So, okay, these are the next two. There's no 4-digit number because this is only one with 3 7s in it. Now we go into the 5-digit numbers. When you try, when the 7 goes into this, it turns out that it doesn't. 7 doesn't go into this. Because 6, 7, 6, when you divide this by 7, it doesn't go into it. But when you try this is equal to, actually 7 does go into this. It's 1, 0, 9, 7 times 9 is 63. You get 4, 7, 6. 6 times 7 is 42, and there's a 5. Right. So that's it. So we have come to there's only one 5-digit number, no 4-digit number, so this is the answer. We're looking for the smallest. It's got 3 7s. It's a multiple of 3, therefore. It ends in 76, so it's a multiple of 4, so it's a multiple of 3 times 4, which is 12, and it's also a multiple of 7, so it's a multiple of 12 times 7, which is 84. Okay, so that's the answer. If we go on to the next problem. Okay, while we are there, maybe we should say something about the divisibility rules. Okay, let me get back to my starting point. New share. Oh, okay. I said we'll go on. We'll say something about the divisibility rules. So just let's go to the next page. The rules for divisibility. I'm not going to go through all most of them. You will know, like 5 and 6, 7. There's no rule. 8. You take the last 3 digits. And you see whether 8 is a factor of the last 3 digits. So this is the rule for 8. The rule for 9. 9, I think most of you know. 9 must be a factor of the sum of the digits. Very similar to 3. Right? If 3 is a factor of the sum of the digits, then it's a multiple of 3. The same thing happens with 9. Though that particular rule only applies to 3 and 9, that the sum of the digits is a multiple of 3, or if it's a multiple of 9, then you can say 3 or 9 is a factor. It doesn't apply to the other ones. So just be careful with that. 10 is easy. 11 is the only one which is interesting. I don't know how many of you know the 11 one. But the way to do the 11 is, suppose you take a number like take a number like this. And you want to know, is 11 a factor of this? Is there a rule? Is there a way of doing it? Well, the way to do this is you add the alternate numbers. 7 and 4, 4 and 9, 9 and 2. Add. What do you have? 11, 20, 22. Right. And then you also add the other alternates, the remaining alternates. 5, 3, 5. Right? Okay, there you get 13. Then what you do is you subtract the smaller one from the larger one. And you ask whether 11 is a factor of that. If yes, then 11 is a factor. Is a factor. Otherwise, it's not a factor. So this is a very quick way of determining whether a number is divisible by 11 or not. Like if you take, for instance, if you take 649, 6 and 9 is 15. The other one, you only got 1 there. 15 minus 4 is 11. So 11 is a factor of this. And if you check it out, this is 11 times 59. See? So this way you can check to see whether 11 is a divisible. This occurs quite often. I don't know whether they ask this. They probably will ask this kind of question in third round to check to see whether you know divisibility by 11, because it's one of those facts that any mathematics student should have in his kit bag, mathematical kit bag. So this is the rule for divisibility by 11. Okay, so I'll just stop there with rules and get on to the let's get back to my questions. Okay, we're going on to question 8 now. Now, question 8, I'm going to assume that you've been through this thing. I asked you to do it the last time. You've got a tray. These are supposed to be pizzas. And the tray, they make these pizzas in such a way that if you take the small one and a small pizza and a large pizza, they fit exactly into the tray. See, no space left over. So this just barely touches it, right? And the question is, if you know that one pizza is 20 centimeters wide and the other one is 30 centimeters wide, the question is, what is the length of the tray? Right? Knowing that these pizzas are, their diameters of these circular pizzas are 20 and 30 respectively. Okay, so let's just go straight into that problem. And okay, usually I find it quite difficult to draw these things. Maybe I can just draw the circles first. Okay, and then you make one circle touch the other one. And then we'll draw a rectangle around this. Let me just draw a rectangle and see whether I can slide it to fit exactly onto this. Hey, I'm not doing too badly. I'm learning a bit here. Wow. No, not quite. Here we go, here we go. Oh, I can give myself a clap. Hey, I've never tried this before, but it worked. So this is the figure that we have. Now, the question is, what is the length of this thing? We know that this diameter is 10, and this diameter is 30. All right, now before we go on, I just want to make some interesting remarks here, useful remarks. The first one is the following. Many of you have not done circles, so let me tell you a few important facts about circles. Right, if I got a straight line and I have a circle, one of my students told me how to draw a circle. You have to hold on to this, the shift key. Right, if a straight line touches a circle like this, right, just barely touches it, it's like the wheel of a car just touches the ground, right? And ideally it touches it at exactly one point. So if you got a circle which is just touching this, then you call this straight line, all right, what do you call this straight line?
Tangent.
A tangent, very good, right. Now, so that's the tangent. There is a point of contact. Let's just locate it. So that's a single point, an important point is a point of contact. And there's also the center of the circle. That's another important point in this diagram, the center of the circle and the point of contact. Now, if you join that center to the point of contact, you get a little line segment. Anybody knows where I'm going to? What's the conclusion?
Is it a 90 degrees angle?
The angle formed between the radius, this is the radius here,
Yeah.
the particular radius which joins the center to the point of contact, that radius to the tangent is perpendicular. Who said that? Just say that again. I just want to see who said that.
Yeah, I said it's
Okay,
90
Pete.
degrees.
Pete, right, you are quite right. Now, the question is now, I don't know, a lot of people know this when you're in grade 11, grade 12, that the radius is always perpendicular to the tangent at the point of contact. But Pete, can you explain to me why? How do you know that's perpendicular? Or anybody?
I'm not sure, but I know that the angle between the radius and the tangent also always has to be perpendicular. I know it's like a theorem, but I'm not sure exactly why.
Yeah, but okay, that is a theorem or whatever, but do you know how to prove it? That's the question. Why? How do you know that does?
I'm not sure.
Anybody wants to suggest a way? How do I know that this angle is 90 degrees?
I think it's because the tangent has to be a straight line, because if it isn't, it will touch the circle twice.
Yeah, but the straight lineness does not
Oh.
give you the 90 degrees.
Prof, do you not prove it
All you know is
by
that you got a probe. You know, the
creating
sum of the two
triangles?
is 180. You don't know that they're equal. Somebody was saying something. Can I?
Prof, what I said was, do not prove it by creating two identical isosceles triangles.
Okay. Yeah, but if you, how do you do it?
Do not create a line from the center to the end of each side of the tangent.
Yeah, all right. You can make them equal, but the problem is you'll have. I know what you're saying. You're saying, okay, just join that and make another one which is equal to this, right? Now you got, okay, this will be equal to this, and you got a common, but you don't have the third condition for congruency because we don't know these are 90 degrees. All right, I'm being a little bit difficult with you guys because I think very few people question this thing. Now, I'm a mathematician, so I never accept anything without a reason. I'd like to know why. Most teachers will just say this and say, okay, guys, I'm telling you so therefore it is true. Okay, there's a reason. Take this point, the center, and join it to any point on the tangent. Right? Join it to any point. Now, compare the size of the red line against the size of the black line. Which is bigger?
The red line.
Okay, Janet, and what's the reason for that?
You can see it's bigger.
You can see
it
it
extends, it extends. So the black line only extends to the end of the edge of the circle. The red line extends out of it.
Okay, you got the idea, but just explain it a little bit more clearly.
The hypotenuse.
Ahmed?
It's the hypotenuse of the triangle, which is the longest.
You don't know its hypotenuse because you don't know that's 90 degrees, Mehmet.
It is a. It is. I don't know. I forgot what it was called.
Anybody? All right, I'll tell you.
Black line, not the radius, and then the red line is the radius plus.
Karen. Now you can see. This is the radius, right? And this is the radius plus something else. So it must be larger. Right? This part from here to here is a radius. Right? So this is longer than the radius, you can see. And that is the radius. So therefore, this is longer. So the conclusion is that no matter which line you take, this will always be longer because every other line will cut the circle. So therefore, it's a radius plus something. So this is the shortest, right? So now we have concluded now that this line here that joins the center of the circle to the point of contact is the shortest possible line that you can draw. And that is one of Euclid's axioms, which says that the shortest distance from a point to a line is the perpendicular distance. See? So because it is the shortest, it's perpendicular. All right. So therefore, this angle is 90 degrees. Okay, so this is the first theorem. Now there is another interesting result which I need to say here. Oh, this should have been a tangent here. So it wasn't that good, huh? Anyway, this is also a tangent here. Imagine it's going to touch. Okay, there's another thing that I need to say, and that is the following. The statement is about two circles which touch each other. Okay. Right, so when two circles touch each other, there are 3 points which play an important role in this diagram. And the 3 points are, can you tell me? The center of one circle is 1 point. Center of another circle, and the point where they touch, right? Those 3 points are associated with 2 circles which touch each other. Now, one can prove that these 3 points all lie on the same straight line. You see, 2 points always lie on the same straight line. 3 points need not necessarily be so. So you got 3 points here. And I tell you that you can prove that these 3 points lie on the same straight line. Anybody wants to try that? To try to prove that these 3 points are collinear. Use the word collinear for this.
Prof, could you not use that the radiuses from each of the centers to that point?
Right. Okay, so let's join the radii. So you can join that and join that. Now, how do I know that the angle that they make is 180 degrees?
Due to the tangent to a circle.
Right, you draw a tangent to the
being
circle.
90.
And there's only one tangent because they both touch each other. So there is what you call a common tangent. Right? So let's just draw that common tangent. It need not be very accurate. There we go. So there is a line which is tangent to both circles. And now from this point onwards, it's easy, right? Do you agree?
Yes, Prof.
Yeah.
Because
The construction is draw the common tangent. And now you can see each of these is 90 degrees from what I just said now, right? This angle is 90 and that angle is 90 because this is a tangent to both circles. And therefore the angle here is 180 degrees, which makes the thing a straight line. Okay, so that's another important fact. Okay. So that will allow me now to calculate this. Let's just get rid of all these guys here. I needed those to do. You see, a lot of times people just take these things for granted, but I was not willing to take it for granted. Now, here the whole question is to find this length here. That is the problem. What is that? We know the diameters of each of the circles. All right, the first thing we do is take the centers. And let's just join these centers to this point here. That's a natural thing to do. And this thing here also. Sorry, this is supposed to be touching, but you can pretend it is touching. All right. Now, so this line that we're looking for, it consists of 3 pieces. Do we know any of those lengths? All right, let's have a look at this small guy. I'm going to take the small guy and join it to do the same to the other tangent. Now I have a little picture there in the corner. What kind of a shape is that? This corner here, this one here, this quadrilateral.
A square.
Is it a square? Who said that?
Me, sir.
Okay, Chantal, tell me why you say it's a square.
Because the two radii are the same length.
All right, so just part of the story. That's not sufficient to say it's a square. Okay, so these are equal, right? That's not enough to say it's a square, right? You can have lots of quadrilaterals. We need more information. Anybody else wants to join, help?
Because the tangent and the radii form 90-degree
Okay,
angles.
so these are 90. Right, so we've got a little bit more information. Is that enough to say it's a square?
And we already know that the other corner is 90-degree because it's a rectangle.
We already know that this is 90 degrees.
Yeah.
We have said that the outside thing is a rectangle. Okay, is that enough to say it's a square?
Well, you have to know that all the sides are equal also. So it's not enough yet.
Okay, Pete, you can calculate the fourth angle.
Yeah, that's also 90 then.
Okay, so so this angle here, because the four angles are up to 360. Now we have something about this picture. What kind of a figure is that? The four angles are 90 degrees. What do you call a quadrilateral with all the angles 90 degrees?
Rectangle.
A rectangle. So we are nearly there, right? But it's a rectangle with two of the adjacent sides equal. Right?
No.
Right?
Which makes it a square.
Therefore, it's a square, right?
Yeah.
Okay. We don't assume anything in geometry. You must take everything one by one. And in the same breath, we might be able to show that this thing here. Let me just yeah, in the same way, we can show that this thing here is a square, right? At the other corner. It's the same story. Just the whole story is repeated here. Okay, but now, do we know any of these three pieces? Remember the radius, we know the diameter of the small circle is 10 and the diameter of the large circle is 30. Those are the only two pieces of information we've got. So do you know any of these small pieces here? There are many people who are silent here. Just a few people talk. I'd like to hear more voices. We have 37 people in the class. It's nice to see so many of you. For instance, don't I know this piece here?
Sir,
Yes, Renono. What is this equal to?
the diameter of the small circle is
10.
the diameter of the small circle is 20, not 10.
Oh, is it 20, is it?
Yes.
Oh, I see. Okay, thank you for that. All right, so, okay, so do we know this piece here?
Therefore, it's 10 because it's the radius.
Yeah, because it's a rectangle. It's a parallelogram. The opposite sides are equal, right? Isn't it? So we know that this is 10 because the diameter, as I don't know pointed out, is 10. So therefore the radius is 10 here. I mean, the diameter is 20 and opposite sides of a rectangle are equal. So this is 10. Right. Likewise, what will this part here be?
15.
15. All right. So we've got 2 of them. The only thing now we need is this third one. So how do we calculate the third one?
You can draw a line from the middle of both circles.
Right.
Between
Okay. That's a good one. Who said that?
me, Sebastian.
Okay, Sebastian. I like that. That's a very important construction. You join the centers. Earlier on, I told you that when you join the centers, it goes through this point of contact. So when you join the centers, do you know the length of this red line that I've drawn?
Yes, that'll be 25 because it's the sum of the 2 radiuses.
Well, yeah, it'll be 25. Because now you can add them. You see, it's a straight line. Otherwise, you wouldn't be able to do that. We know it's a straight line because we proved it. So therefore, this red line is 25. Okay, we're kind of getting there. What we want is this. We got a piece here, we got a red line here, and you got another piece here. How do we get to this?
You can draw a line straight down.
Now draw a line straight down. Okay, I like that. So what you do is, but straight down you are, if you use mathematical language, who said that?
I did.
Okay, Laura. Yeah, but if you use mathematical language, what you are saying is you draw a perpendicular to this line, isn't it?
Yes.
Now you draw a perpendicular, clever, because now you got a right angle triangle. This one here is a right angle triangle, and you know the hypotenuse.
So can't you use Pythagoras to work out the straight line down, the perpendicular line?
You can work out Pythagoras to work the same, but you need to know this first.
So the distance from the perpendicular line down to the side of the rectangle is 10. So you take the 15 and you subtract the 10.
Why? How do you know that this is 10?
So because that's from the middle of the small circle.
No, just this piece here. You see, you know this whole thing is 15. 15. That's, you know, from the middle of small, that's 15, right? You said you are subtracting 10. How do you know that this is 10?
Due to dropping the perpendicular and opposite sides being equal, the radius
Why are the
above
opposite sides equal?
the bottom, due to it being a parallelogram.
How do you know it's a parallelogram?
Due to dropping the perpendicular and the box being a rectangle.
It's a rectangle, right? That's why. Because this is 90 degrees. We already know that this is 90 degrees, right? We know that that is 90 degrees. So again, you've got 3 angles of a quadrilateral 90 degrees. It must be a rectangle. The fourth one will also be 90. So therefore, it's a parallelogram. And therefore, this part here will be 10. And if that is 10, the whole thing is 15. As Chantal correctly said, this has to be 5. But you have to first show that this is equal to that. And the reason why it's equal is that this is a rectangle. The reason why this is a rectangle is that 3 of the angles are 90 degrees. See? See, in geometry, you must justify everything. Nothing, don't ever take anything for granted. Otherwise, you can get into trouble. All right, so now we've got this. We got by Pythagoras, this is 25, this is 5. So this question mark is actually equal to this. Why is this equal to this?
Opposite sides equal in a rectangle.
Again, it's the opposite sides of a rectangle. So the question mark is equal to this side here, and that's the square root of 25 squared minus 5 squared. Okay, now if you can use, by the way, you can use difference of two squares. A squared minus b squared. Very useful in Pythagoras. 25 minus 5 into 25 plus 5. 25 minus 5, you don't need a calculator for that. 25 plus 5, you don't need a calculator for that. So it's the square root of 20 times 30. 10 occurs twice, you can take it out, and 2 times 3 is 6. So therefore, this question mark is 10 times square root of 6. And so that gives me the answer. The answer is, we all have all three pieces, is 10 plus 15, which is 25, plus 10 times square root of 6. That cannot be simplified. So that's that length. Okay, thank you. I think we had a lot of nice contributions there. And this is geometry, so that is why I'm taking it easy, and I'm going to, and I'm showing you how to do geometry. You must do it. Okay, is that all? I think that's the only question. Was there another question? I'm not sure. Let me just check. Get back to the question. Oh, there's more to it, I think. The A and B. So what is the length of the tray? Right, we've just worked that out. Now B, I'm going to explain. I'm not going to read through that. I'm just going to tell you what the question is. Go back to my whiteboard. Now here, this question says the following. It says that you have two types of pizzas. One is a square. Hey. Okay, let me just get rid of that rascal. And I want to draw a circle. Okay, you can have a round pizza, or you can have a square pizza. Now, you put the square pizza in, the round pizza into the square pizza, and they both got the same. One has got. They both got the same diameter. This diameter of this is equal to the side of the square. All right. So you got a square pizza, and you got a round pizza, and the diameter is equal to the side of the square. So let me just draw a square. Oui. Okay, now I can take this thing and okay, so this thing fits exactly into that because the diameter and this are the same. I'm trying to make it fit, but I guess I'm not going to worry too much about it. Okay, so Sorry, I'm not sure what happened here. All right. So the question is now, this pizza here, it's just imagine it fits snugly into the square, which it doesn't. The waiter says, you know, the square is 30%. Its size is 30% more than the amount of pizza you will get on the circular pizza. The square pizza has got 30% more. And the question is he correct? How accurate is he? Is he exaggerating it, or is he? I can't understand what the heck is going on here. Sorry. Oh, anyway, I think once I've taken it out, it's gone. All right, now I'm sorry about this. I can't draw it very accurately. So the question is now, is the area of the square and the area of the diameter? We need to calculate to find out whether that area of the square is 30% more than the area of the circle. Right? That is really the question under investigation. Right. Let's try to investigate that. Now, we don't know what the diameter is, so we'll have to just assume that it's R. So let the diameter be equal to don't call it R, we'll call it D for diameter. Right. Or maybe we better say let the radius be. It's much better to use a symbol for the radius. The radius equal to R. All right, so if the radius is R, the distance from here to here will be 2R. Right, so we know, give a symbol for the radius, then we know the area of the square. So the area of the square is equal to 4R squared. Right, okay, now we need to compare that with the area of the circle. The radius of the circle is R, so the area of the circle is pi R squared. Okay. So if you want to find out how much more is the circle, the square larger than the circle, why don't we just work out the ratio of the square, that area, over this to see how much larger it is. So the area of the square over the area of the circle is actually equal to 4 over pi. You see, pi is 3 1/7. So we can multiply numerator and denominator by 7. And here you get 22. Pi is 22 over 7. So multiply numerator and denominator, simplify that, you get 14 over 11. And make that into a decimal. 11 goes into 30 2 times. Then you have 80. 11 goes into 87 times. 11, 7, 77, and so on. So the ratio of the square to the circle is 1.27, right? Which means that the square, you see, this is 27% more than one. This is 1 in 27 over 100, right? So therefore, the square its area is 27% more than, approximately. right? So the waiter said, it's 30%. So he was nearly right, but he was overrating it. So the question here is, I'm not sure what the question is, but it's asking about whether his estimation of 30%, whether it's more or less or whatever it is. Now we know what that actual value is, it's 27%. So we can go ahead and answer that question, whatever that question is. They claim that the square pizza gives you 30% more. Is this 30% figure exactly correct, an exaggeration or an understatement? The answer is, it is a exaggeration, because it's actually 27%. And you must prove your answer, which we just did. Okay, so let's just get to the next question. Okay, now we're now going on to question 9. Question 9, let's read it. SIPO writes down all the 7-digit numbers that have their digits increasing from left to right. So you got an example here. From left to right, it's increasing. 1, 2, 3, 4, 5, 6, 80, but it must be a 7-digit number. But this one here, is not acceptable because it's not increasing. And this too is not increasing because it's increasing. Now, yeah, it's not increasing. We should have said they are distinct numbers. All right. So, and leading zeros are not allowed. Obviously, it's a 7-digit number. You can't have a 0 in front. Right. The question is, how many numbers does SIPO write down? He writes down the whole lot, all of them. So how many does he write? I'm going to go back to my whiteboard, because I've got a couple of things to say about this. Let's have a look at this problem. You're writing down 7-digit numbers, all in increasing order. So if you take 1, 2, 3, say 4, take 6, 7, and 9. That's an example of a 7-digit number with increasing numbers. I want to count how many are there altogether. Now that you will say, hey, this is going to be very difficult. How do we count this thing? You have to write down every possible combination, and you can be very complicated, right? So you have to build up strategy. Anybody can think of a strategy? All right, I'm going to say the following. Rather than look at the 7-digit number, why don't we look at all the numbers from 1 to 9, the whole lot? So when you write these things down, there are 2 numbers missing. Which are the 2 numbers which are missing? 5 and
8.
8. Do you agree that to write a 7-digit number down to all the numbers increasing, all I have to do is, from those 9 digits, what do I have to do?
Eliminate 2 numbers.
Remove 2, right, Karan? Very good. So to create a 7-digit number, I'm not going to write down all of them. I'm going to say, to create it, I'll write down the whole lot from 1 to 9 and take out 2. So the number of numbers that we can create is exactly equal to the number of ways in which you can remove 2 numbers from 9. I'll repeat that. The number of 7-digit numbers that you can create, right? I can count it in a different way by saying I'll remove 2 digits from 9 digits. Each time I remove 2 digits from 9 digits, then I have a 7-digit number with increasing, which are all increasing. So the number of ways, let me just choose the black here. The number of 7-digit numbers that we're looking for is equal to, now this is a very powerful statement, is equal to the number of ways 2 digits can be selected from 9 digits. Each time I select 2, like I select 5 and 8, I've got a 7-digit number. If I select 2 and 9, remove them, you got a 7-digit number. If I select 4 and 6, remove them, I've got a 7-digit number. All the numbers are increasing. And conversely, whenever you have a 7-digit number, it is actually obtained by removing 2 digits from this thing. So in other words, they both give you the same count. So now the question is, how many ways can you choose 2 digits from 9 digits? So you can choose it like this. You can choose 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 1 and 7, 1 and 8, 1 and 9. If you insist that 1 is one of those numbers, how many are there altogether here? 8. 2, 3, 4, 5, 6, 7, 8, 9. Right? So there's just 8 of them. Right now, if it starts with, if you insist that 2 is removed, you're not going to go back to 2, 1 now. Then 2 being the smaller of those 2, then you can have 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9. And there you have 7 of them. Okay, so that takes care of the 3's. And you can do the same thing with the numbers. If you remove 3, 4, 3, 5, 3, 6, 3, 7, 3, 8, 3, 9, there's another 6. So you can go on like this. So how many pairs are there? It's 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. You have, at the last stage, you have 8. The first digit is 8, which you remove, and 9. That's the only way you can have an 8 in it. So that gives you the 1. So the total number of ways in which you can select 2 numbers from 9 numbers is all this. Right? You can actually count them. And when you add up all these, right, you're going to have, actually you have 36. 10, 15, 21, 28, 36. Now, while I'm here, I'm going to show you this 36 is actually 9. You're taking 2 numbers from 9. You take 9 times 8 and divide it by 2. 72 divided by 2. Now, this is just an observation. And it always happens like this. If I had 50 numbers and I want to choose 2, here you had 9 numbers, 9 times 8 divided by 2. If I had 50 numbers and I want to choose 2 of those 50 numbers, how many ways can I select 2 objects, if you like, from 50 objects? The answer is 50 times 49 divided by 1 times 2. Very useful formula. See, it's a large number, 1,225. So if you had 50 objects and you want to select 2, there are many, many ways of doing it, right? And if you were to start counting them, yeah, in this case we can actually count them, so it's not a problem. But in the general case, it's difficult to count it. So in that case, you have to figure out a method of actually solving that problem, right? How many ways can you select 2 objects from n objects? Now you can count them like the way I did just now with 8, with 9 objects. And you remember we started off with the first number was 8. So here it will be n minus 1, right? You pair off 1, the number 1, with the rest of them. There are n minus 1 of them. And then you add to that the one smaller than that we had 7. And then you add to that 6. But now you got n. We don't know what n is. N could be 50 or 100, a million. And now you just put dot, dot, dot because we don't know how many there are. But in the end, you'll have, as we saw, 2 plus 1. So this is the answer. The number of objects that you can choose from, number of ways in which you can choose 2 objects from n objects is this. Now, how can, I said that this is actually, this thing here is going to be equal to, I said n, which is 50 or 8 or 9 or whatever, times the one just below that, over 2. Now, how do I know that this is equal to this? It's an interesting question. So you're adding n minus 1 and the one below that and the one below that all the way until you come to 1. I don't know what the value of that is. And I'm going to prove now to you that when you add up all these, you're going to get this. Very interesting. So we don't know what that is. Let's call it x. I'm going to take the same thing and write it backwards. Put 1 in the front. 1 plus 2 plus 3. Put them under each other, right? And you'll end up with n minus 2. I'm writing it backwards. Plus n minus 1. It's a very important step. When you got something like this, you write it backwards, it'll give you the same answer. Whether you write it, add from top to bottom or from bottom to top, there's no difference. And now what you do is you add these 2 equations. Right? What is x plus x? It's 2x, right? Add these, what do you get? Come on, guys. What is n minus 1 plus 1?
n.
N. Plus. Add these, what do you get?
N.
N. Add these, what do you get?
N.
Isn't that amazing? And here, what if you add these, what do you get?
N.
And here,
Another one.
Still n.
so you got lots of n's. But how many of them do you have? We did the count right in the front. The 1, 2, 3, 4. You got n minus 1, isn't it?
N.
N minus 1, because there's a count 1, 2, 3, 4 up to n minus 1. So the n such numbers there. So I'm sorry, n minus 1. So there'll be n minus 1 of these as well. So you got n minus 1 n's. And what is that? That is n minus 1 times n. 6 n's is 6n. 8 n's is 8n. N minus 1 n's is n minus 1 times n. And that is 2x. So what is x equal to? Bingo. See? Now, the moral of the story is, it's a very important fact, very, very important fact. You must always remember this. I proved it for you. So you must remember it as a fact. The number of ways of selecting two objects from n objects equals n times n minus 1 over 2. Very important. Now, what you should do is go to the book. And I think I have, I'm not sure exactly what the thing is. I think the chapter is called counting. Something about counting. Counting. There's a whole chapter on it, how to count. And I hope I've inspired you sufficiently to see how you can count. And if you go through that, now you guys are good students, you're in round 3. So go to that and read the whole thing from beginning to end. Slowly, read it, and you'll have lots of tricks on how to count. Okay, this is my book. Okay. Okay, let me just go down. All right, I told you how to, let's just search for counting. So I put Control F, that's a search, and I type counting. I don't know whether I'll get to it. Counting. All right. And when you go to counting, there will be a lesson, something about counting. I don't know which lesson it is, and it takes a while to do that. All right, so while it's doing that, let's get back to our question. You don't have it in front of you. Can you all see the screen from the book? You're sharing that, isn't it?
Yes, Prof.
Right, okay. Now,
Yes.
the question, let's go back to the question while it's doing that. They say one of these numbers is chosen at random. In other words, those 36 numbers, we are in the same problem. One of those 36 numbers is chosen at random. And the question is, what is the probability that its 100th digit is a 5? Right? Think about that. This thing is chosen at random. And what is the probability that its 100th digit is 5? The thing is very slow because I think we in Zoom, it doesn't respond very well. Oh, it's 160. Oh my God, it's 165 of them. Ooh, no wonder it took such a long time. Sorry. Maybe I should do something else here. Oh, you're right there. Here you are. Lesson 3. Okay. Such functions, counting and probability. And it's on page 176. So if I go up to, there's 637 pages in this book, guys. Look at this. We're going to go to page 176. So I'll put 176 there and press enter. There we go. Okay. So you've got, is this 176? It doesn't look like it's 176. I don't know what happened here. But anyway. Oh, there it is, right. You see? So I discuss a lot of things, a little bit of sets, Venn diagrams, all this are all very interesting. So read all this. And then functions, you learn about functions. If you haven't already done that, and I say something about functions, a little more advanced kind of things, it might be a little bit more. You can skip that if you want. And then here, the counting starts here, 3.3. And you got all different problems about how to count. The first counting principle, the second counting principle. Lots of lovely examples, right? And arrangements and permutations. Just go through all these things. The factorial notation is introduced here. I think some of you already know about factorials, and a lot of things here which tell you. Now I've got R element subsets of a set, and while we do that, we have this thing here, a rather complicated thing. Yeah, you need to select 4 vertices from octagon how many ways. So you got that kind of a thing. So you got a lot of other things here, but somewhere in this, I've discussed this business of 2 objects at a time. So I just got that to illustrate that you can go to the book and learn much more about counting than what I have just exhibited. Let's get back to this problem that we're looking at. The problem says that one of the numbers is, you got 36 numbers, which we have, which are in increasing order, numbers of 7. And now you may have a number like 1, 3, 4, 5, 7, 8, 9, if you're living out 2 and 6, for instance. Now, they say that what is the probability that if you pick any one of the 36 numbers, that 5 is in the 100th position? Now, this example here that I've taken, 5 is in the 1000th position. So what is the probability that 5 is in the 100th position? Now, for 5 to be in the 100th position, 5 will have to be here. So what are the chances that 5 will be, if you pick a number at random, there are 36 choices. Right? How many of those have got a 5 in the 100th position? If you know that, then you can work out the probability. Okay, so how many have got a 5 here? Now, if this is 5, remember they're all increasing. What's the conclusion? The conclusion is that we should know exactly what the first 4 are, isn't it? It's the 5th number, and it's increasing. So you must have 1, 2, 3, 4, 5 here. That's the only way you can have 5 in the 100th position. Do you agree? So we are looking for all the numbers which starts with 1, 2, 3, 4, 5, right? Only in those numbers will you have 5 in the 100th position. Because if this is 5, then all these will have to be, it's increasing. So it has to be 1, 2, 3, 4. So now, how many such numbers are there? Now you can have a lot of choices here. All right, let's see. Which numbers go in here? You got 2 numbers, 6, 7, 8, 9. And you got 2 numbers which are chosen from these 4 numbers. And you have to choose 2 numbers from those 4 numbers. I just told you how to choose. The number of ways of choosing 2 numbers from 4 numbers is 4 times 3 divided by 2, and that is 6. But in this case, you can actually write down which are the 6 numbers. You can have 67, 68, 69. Those can be the endings, or it could be 78, or 79, those which start with 7, and finally, those which start with 8, 89, and that's it. There are no more numbers which can fit into this lot, and there are 6 of them. So if you pick the numbers at random, there are only 6 of them which have a 5 in the 100th position. So the probability, the only 6 possible ways of getting success, probability is 6 out of 36. See? Because there are only 6 ways, only 6 possibilities where the 5 is in the 100th position. So the chances of getting that are 6 out of 36. And the chances are, if you like, 1 in 6, 1:6, or 1/6, or whatever way you want to write it. Okay, so I know you probably don't know much about probability, but the probability is, although it's a big word, the probability just means how many are there altogether and what are the chances of. See, like for instance, if you have in a school there are 100 boys and 100 girls, and you pick a person, a learner at random, what is the probability that it's a boy? You have 100 boys and 100 girls. What is the probability? It's a boy.
50%.
50%, because you are saying it's 100 out of 200. But suppose you had 100 boys and 300 girls. What is the probability that you're going to pick a boy?
25%.
25%, because now it's 100 out of 400. It's the same thing here. You got 6 out of 36, right? So that is how you calculate probability. It's a very simple principle, but you must just understand you have a feeling of what probability is. Okay, so let's get on to the next problem. Next problem is go back to my question. Okay, so there's 6 out of 36, you can see. Okay, now we go on to question 10 now. Question 10, very interesting question. It says the following. If you add the reciprocals mean, what is the reciprocal of 6? The answer is 1/6. The reciprocal of 10 is 1/10. Just excuse me, my room has become dark. All right, so if you add the reciprocals of any 2 consecutive odd numbers, the numerator and denominator of the resulting fraction will be the shorter sides of a right-angled triangle of which the hypotenuse is an integer. Now that's a long story there. Now let me just illustrate this, what they are saying. Go back to my whiteboard. Okay, so what we are saying here is, if you take the reciprocals of 2 consecutive odd numbers, now the examples of 2 consecutive numbers are 3, 5, maybe 7, 9, maybe 13, 15, like that. Consecutive odd numbers. If you take the reciprocals and add them up, this case is 1/7 plus 1/9. Here it's 1/13 plus 1/15. Right? They say that, let's add them up, and what do you get? Here you get 15, and 3 plus 5 is 8. Here you get 63. LCM of 7 and 9 is 63, the product, and it's 7 plus 9. And here the LCM of 13 and 15 is 13 times 15, And here you get 28. They say the example that they took, there was 5 and 7, I think, or maybe the same one, 1/3 and 1/5. All right, now in each of these cases, you got two numbers, and what they are saying here is that I'm going to draw this freehand. Oh, this freehand is not that nice. Anyway. They say that these two, 8 and 15, are the sides of a right angle triangle. But when you got two sides of a right angle triangle, the third side need not be an integer. You know, I mean, you know that. If you got square root of, if you had 1 and 1, for instance, you get square root of 2. So it need not be an integer. But they say here that this will always be an integer. That's the interesting thing. See, in this case here, if you work out 8 squared plus 15 squared, you'll actually get 289, which is 17 squared. It's an integer. Now here, if you try 16 and 63, and if you let one side be 16 and one side be 63, and if you calculate this, you actually get 65, because you get 16 squared plus 63 squared, which is 256 plus 3,969. I just happen to know my squares quite well, which is 4,225, and that is 65 squared. So you actually get 65 squared here. And this one, I must confess I don't know what this is. So 28, 195, and there's something else, and that turns out to be an integer. All right, I do know that 195 squared is 3, and 28 squared is 784. So this is 39809. So I suspect it's going to be 197. I can't be sure. Anyway, now they ask you to prove that this always happens. Prove that the hypotenuse is always an integer. Now, how do you go around proving this? Well, the problem is now you have to take two consecutive odd numbers and you have to take random numbers. You can't just take two specific examples and say, well, it works here in these 3 examples or 4 examples, therefore it must work for all. Mathematics doesn't work that way. You must try to prove it for every conceivable case, no matter which 2 odd numbers you take, consecutive odd numbers, 1,000,001 and 1,000,003, you should be able to conclude that if you draw a right angle triangle with those 2 sides, the hypotenuse is an integer. So you have a general thing now. So you got 2 consecutive odd numbers. Now between, this is how we're going to prove this thing now. I'm going to prove this. Okay, you got consecutive odd numbers, right? So in between those consecutive numbers, what number have you got? What kind of number do you have? You have an even number, isn't it? Come on, guys. You got 2 consecutive odd numbers. So you have an even number in between them. I'm going to take those 2 consecutive numbers, but there is something in between here. That number is even because this is odd, and this is even. Now, how do you write a general even number? Right? I don't know what it is. I'm going to call it 2n. All even numbers can be written as 2 times something. Right, now these are consecutive. So the one just before that will be 2n minus 1. And this is 2n plus 1. Okay, so what am I doing now? I'm taking the reciprocals of these numbers. So I'm taking 1 over 2n minus 1. That's that. And I'm adding it to 1 over 2n plus 1. Right, now this is algebra, and you are going to simplify this thing. Common denominator, this, some of you in grade 6, you might not have seen this before. It's just like adding any two fractions. Maybe I'd better put it underneath here so that you have a clearer picture. Right. So you take the LCM of these two, you got, or any, this thing here, both of them go into this. 2n minus 1 goes into this 2n plus 1 times, plus 2n plus 1 goes into this 2n minus 1 times. 1. Okay, the 1 and the minus 1 cancels off, and you have 4n over. And at the bottom, I'm going to expand that. This is a minus b into a plus b. So that's a squared minus b squared. So it's 2n all squared, which is 4n squared, minus 1 squared, which is minus 1. So this is where we are. And now we need to prove that when you take I'm going to draw a decent right angle triangle here. Okay, we're going to prove why is this thing? We're going to say that if one of the sides is 4n and the other is going to be 4n squared minus 1, this will always be an integer, this thing here. All right, now we can calculate this. We can calculate the hypotenuse, let's call it h. Now what is h squared? Hypotenuse squared is 4n all squared plus 4n squared minus 1 all squared, right? That squared is equal to that squared plus that squared. Now let's calculate this algebra here. 4n, if you square it, you're going to get 16n squared. And this is a square of a subtraction sum. So you square the first term, 4n squared, if you square it, you get 16n to the fourth. 4n squared times 4n squared. Then you multiply these two out together, you get minus 4n squared, and you must double that. You get minus 8n squared. So you multiply these two and double it, and then square the negative 1, and it becomes plus 1. And when you simplify this, you have a 16n to the fourth here. 16n squared minus 8n squared becomes plus 8n squared. 16 minus 8, 8n squared, plus 1. Now watch. See, the square of 4n squared minus 1 is this. And this one here looks almost exactly like that. And that is actually 4n squared plus 1 all squared. This quantity here. Okay, sorry, I have to move off to that. So that is h squared. So h would be equal to 4n squared plus 1. And that's a nice integer because n was an integer. See? All right, so the hypotenuse is 4n squared plus 1, where n is the average of these two numbers. Well, it's not the average, it's actually half the average. Or otherwise, it's a square of the middle term plus 1. All right, square of the middle term plus 1. That's your n. Let me just see if that was the case in these previous cases. So here I had 3 and 5, right? What's the middle term? 4. Square it, 16. 16 plus 1, 17. There it is. That's your hypotenuse. You see, we said 2n, you know, we found the middle term. The middle term of this is 8. But That's twice n, so n is 4. Now here the middle term is 8, and that's twice n, so in this case it's 4. You square that, 4 squared, 16 plus 1 is 17. Oh, what happened to this? Oh, I'm sorry. The middle term is 8. 8 squared plus 1 is 64 plus 1 is 65. There it is, 8 squared. And here the middle term is 14. 14 squared plus 1. 14 squared is 196. Yeah, my guess was right. All right. I just approximated this thing here. You know, it's about just past 19 squared, and it ends in a 9. So it must end in a 3 or a 7. And I said, well, it looks like a 7. Okay, so that takes care of this problem. You can see how you prove things, right? Again, I'll just go over this thing again. What you have to do is, the general thing is you say, I don't know what this odd number is, what that one, give it a name. Right? You might have said, let it be equal to x and make this thing x plus 2 or something like that, you know? You could do it like that. And I think you would probably be on the right side, but you need to have it to be an odd number. When you say x, you're not making it an odd number. We don't know what x is. So you have to make it as an even number minus 1, even number plus 1. So you must take this thing here to be 2n. Then only you're using the fact that both of them are odd numbers. But if you call it x, that doesn't help you too much. You might not be able to prove it. Okay. All right, so I didn't ask you too many questions in that one. And the next question, next problem we're going to work in is, let's just go back to our, question paper, or the question. Okay, we are still in, I told you it will take a long time today because I'm teaching you many things. All right, let's look at number 11. This is a question in geometry. And so the problem here is that you have the midpoints of a trapezium. So you got this whole thing here is a trapezium. The opposite sides are parallel, one pair, but the other opposite sides are not parallel. It's a trapezium. You're given two adjacent sides. You're given that this is 4 times square root of 2, and you're given that this is 8 times square root of 2, and you're also given that this is a right angle. Right. You're also given that these points here are all midpoints. The midpoints of the sides of the trapezium are joined. I didn't indicate the midpoint. I don't know how to clutter this thing up, but just remember this is the middle. These are equal, these are equal, these two are equal, those two are equal. And you join all these things and you create a new quadrilateral from the original trapezium. This is a new quadrilateral. First question is prove that this is a parallelogram. Interesting problem. No matter what trapezium you take, as long as it's got a right angle, it's a parallelogram. In fact, if you take any quadrilateral and do this, it's an interesting case. Right? Just note that I'm not writing it down. If you take any quadrilateral and you join the 4 midpoints to create a new quadrilateral, that new quadrilateral is always a parallelogram. Okay? All right. Okay, now you have to prove that it's a parallelogram, and then you have to prove that the area of this parallelogram is half the area of the entire figure. And then they tell you, if you know the area of this parallelogram, calculate that length. So this is quite a demanding problem. I don't have many minutes, so I'm not going to rush through it, but I'm going to take you through the processes. Okay, so let's just go to my whiteboard. Right, the first thing is I'm going to prove what I said earlier on, that it doesn't matter what quadrilateral you have. Any quadrilateral. Like that. I don't want it to look as if they're parallel. Okay. Some quadrilateral like this. Okay, I'm going to prove that if you take the midpoints of the four sides and join them, you'll always have a parallelogram. So if I take the midpoint here, join it to the midpoint here, and take the midpoint here and join it to the midpoint here, and take this midpoint and join it to the midpoint here, and then finally, I just can't get these things right. Join this to the midpoint there. Now you can see this figure does look something like a parallelogram. It always happens as a parallelogram. Okay. Is there anyone who can suggest how can you prove that this is a parallelogram?
Can you use midpoint theorem?
Right, okay. You have to use a midpoint theorem. Now, the grade 8s in this class don't know what the midpoint theorem is. So I'm going to just take a little time to explain to them what the midpoint theorem is. So all these are equally, as I said. Now, the midpoint theorem says the following. The people who are in grade 9 and grade 10, grade 11, they probably will be familiar with the midpoint theorem. It says the following: if you take a random triangle, no matter what triangle you take, right? And if you take the midpoints of two sides of the triangle, I'm approximating the midpoint here, right? If you take the midpoints of two sides of a triangle, so in other words, these lengths are actually equal. These are equal. And if you join these midpoints, you have a very beautiful theorem in geometry. Right. You can make this following conclusion. It's a theorem. This new line that you draw is, in one instance, it is parallel to the third side, as you can see. Now, this is a theorem. It's not obvious. And the second thing is that the length of this line is actually equal to half. This is equal to half of this. See? All right. Now, there are many theorems in parallelograms. In grade 8, they don't do any theorems. I don't know whether they do that. But in grade 9, you will have theorems. And there are mostly in grade 9, you do triangles and congruency. Congruency is a very powerful thing. The two triangles are identically the same under various conditions. So you have conditions under which two triangles are exactly the same. In other words, all the sides and all the angles are equal. So in grade 9, you do congruency. This is what I think happens. And maybe towards the end of grade 9, you start studying parallelograms. That's a four-sided figure, right? Or the opposite sides are parallel. And you have lots of theorems which tell you under which conditions a four-sided figure is a parallelogram. Many conditions. Like I'll just go quickly. What do you mean by parallelogram? Quickly, I'll just say it. Parallelogram is a four-sided figure where the opposite sides are parallel. You can read my book, and I've got all the notes written entirely, right from grade 9 to grade 12. All the theorems of geometry are written there. I've got two whole chapters on that. So you can read through the junior ones, grade 9 and 10, and read through all the theorems there. And these theorems are there. So a parallelogram by definition is a four-sided figure where the opposite sides are parallel. And then you have these interesting results that if you have a four-sided figure and you know that the one pair of opposite sides are equal and that same pair are parallel to each other, right? Then you can conclude that this side is parallel to that side, making it a parallelogram. See? So if you're given this condition, you can conclude it's a parallelogram. There are many conditions, beautiful conditions. Another one is that if you know that the opposite sides are equal, if you know that these are equal, again, you can conclude it's a parallelogram. And conversely, if you know it's a parallelogram, you can conclude this. And if you know it's a parallelogram, you can conclude that. So it works both ways. So if you're asked to show that something is a parallelogram, you can try to show this, or you can try to show this. You see, that the opposite sides are equal, or the other ones, like for instance, if the two diagonals, each one bisects the other, right? If you have the two diagonals of a quadrilateral, like that, where the diagonals bisect each other, then you can conclude that this is a parallelogram also. So there are many theorems like that, which are done in grade 9 and grade 10. All right, so bearing that in mind, where's the midpoint theorem here? I don't have a triangle, so I need to create a triangle to use the midpoint theorem, right? Let me give names to these symbols, A, B, C, D. And let's call this E, F, G, H. Right, now how do I create a triangle here to get midpoints? Any suggestions?
You construct the diagonals.
Okay, but you need to construct just one diagonal. You can take any one diagonal and we construct it. Usually when I have a construction, I put it in a new color, you know? Oh, oops, sorry. All right, now when I join AC, I now have split my original quadrilateral into two triangles, right? You can see a triangle ABC and also a triangle ADC. This red line splits the quadrilateral into two triangles. Now let's look at each triangle. In this triangle, I've got the scenario here. Midpoints are joined, and the theorem says that, the theorem said two things. One is that this is parallel to this, and the other is that EF equals half of AC. EF is equal to half of AC. Right. So from this triangle, if you use the midpoint theorem, you can conclude that this line is parallel to this, and the length of this line is half of this. Now, if you go to the other triangle on this side, what's the conclusion there? Can somebody tell me? I'm talking about this triangle here, ADC.
So the conclusion would be that HG is parallel to AC, which is parallel to EF.
Very good. HG is parallel to AC. That's very good. Almaz is in grade 8. You got a great future, Almaz. So you got HG is parallel to AC. And she also said that AC is parallel to EF. So it means that HG is parallel to EF. You can conclude that. So this line here is parallel to the other two lines. What else can you conclude? Anybody wants to say apart from HG parallel to AC? HG is equal to?
Half AC.
Yes, Chantal. HG is equal to half AC. So you got HG is half the diagonal, the red line, and EF is also equal to half the diagonal. So what's the conclusion?
EF equals
EF is equal to
G.
HG. So now you got this line here is equal to this line here. I'm running out of symbols. So this length is equal to this length and is parallel to that. So in this quadrilateral here, you got one pair of opposite sides are equal in length and they are parallel to each other. You see, this is the one that I was talking about quietly here. Can you see? If you know that one pair of opposite sides are equal and also parallel, you can conclude that this is a parallelogram. And that's exactly what we wanted to conclude, that EFGH is a parallelogram. That follows from the fact that HG is equal to EF, N is parallel to it, and therefore by a theorem in geometry, this figure is a parallelogram. This is a theorem that if you got one pair of opposite sides of a quadrilateral are equal and parallel to each other, then that quadrilateral is a parallelogram. So that proves the first part. The second part of this, I'm going to just do the second part only. I don't want to abuse the time that is given to me. You need to know something like this, which is a useful little thing, which I'm going to tell you. All right, so suppose you go back to this midpoint theorem story. I'm not going to change the color. All right. And then you take three midpoints. You take the midpoint here. Join these midpoints, and then also join these midpoints. And also join these midpoints. See, so if you take the three midpoints of the three sides and join them, you get a new triangle inside. And actually the whole triangle is split four ways. Right? Okay, now I'm going to name these sides as X, Y, and Z. I don't know why I'm struggling to. I'm going to name this one here X, X, X. I'm sorry. Oh, sorry about that. Let's just get this thing neatened up. I wanted to call it X, Y, and Z because they are not equal to each other. It's not an equilateral triangle. So we want this to be Y and this to be Z. Right. Now remember, we got midpoints here. What can you say about X? It's equal to half of what?
BC.
And what is half of BC? Each of these, isn't it? Right? So this must be X. that is x, you see? And likewise, this is y, that turns out to be y, and that turns out to be y. And this is z, this turns out to be z. Because this z here is half of this, again by the midpoint theorem. But this is a midpoint here, so now if you look at this thing here, you will see that those four triangles, what are the three sides of this triangle here that I'm pointing to? What are the three sides of this triangle? Give me the names. X, X, Y, and Z, right? Okay, those are three sides. What are the three sides of this triangle? Again, X, Y, and Z. What about this?
Same.
X, Y, and Z.
And here too. So all four triangles have got the same sides. And when you do congruency, if three sides of one triangle are equal to three sides of another, then you know that those triangles are congruent, isn't it? So all these four triangles are congruent. That's a beautiful thing about this. When you join the three midpoints, you create four congruent triangles. They're all congruent. In fact, there are lots of parallelograms here and so on, right? Which we won't go into. But specifically what I want to say is that because they are congruent, their areas are the same. They got the same area. See? Somebody has got his mic on and we are hearing a laughing at the background. Just take your mic off, please. So the area of this, if you call it Q, the area, all these have the same area. See? Which means that each of these triangles, the area of that is a quarter of the whole triangle. See, each of these is a quarter of the whole triangle. So whenever you have a midpoint theorem, the little triangle here at the top, its area is going to be a quarter of the area of the whole triangle. See? So there is more to say on this, but I'm not going to confuse the issue because if you just go back to the problem at hand, if I just go to this thing, then you share and go to my problem. You see, I'm going to do it here to save time. Okay, if I join this like that, see, and if I call this area here capital P, for instance, if I call this area is P, and if I call this area Q, then P is equal to a quarter of ADB we're talking about the areas here now. This part here, this is what I said. There's it, you got this, you got a midpoint. So that top piece will be a quarter of the area of the full triangle. I'm sorry, that's P. And Q, this thing, will be a quarter of, starting from here, CDB. Okay, so you have this triangle, quarter of that is this, and the other triangle, quarter of that is that. But when you add these two triangles up, you're going to get the area of the entire trapezium. So when you add these two areas, you're going to get P plus Q is equal to a quarter. If you take the quarter out, you're going to get the area of this plus the area of that is the area of this entire trapezium ABCD. So we got that plus that is a quarter of the entire trapezium. And if you call this area R and if you call this area S, for exactly the same reason, R plus S is also another quarter. So when you add the four corners, you get a quarter of the area of the trapezium plus another quarter. So the four areas would add up to half the area of the trapezium. So these four corner areas add up to half the area of the trapezium. So therefore the remaining part would be half the area of the trapezium. That is what we are asked to show here, that the area of this parallelogram is half the area of ABCD. All right, you can see as the problems get more and more, go towards the higher levels, it becomes more and more difficult. But if you know some of these facts, then they will help you to solve the problem. So there are lots of facts that you need to know. And if you try to read some of the things in the book, you'll equip yourself with many things. Let me see now. I can't remember exactly what are the chapters which are relevant, so that you can equip yourself with some material to go into this. Let me just go to new share. Okay. Now, I asked you to get the book. I don't know how many of you managed to get it, but I presume that more people got the book today than what it was last week. So I'm going to refer you to the book now. If you haven't got it still, you can go to, I don't know whether I can remember this thing. It's www. No. I think it's HTTPS. I don't know, something like this. I think you got this. And I remember it was mathematics. And there's an ordinary dash, an Olympiad, and a dash. I think questions, not sure. Oh, there was an N in between. So the slash N, EN, slash that. Okay. If you go to that, it'll take you to the book, and you can purchase it from there. But some of the chapters which you should read, and let me tell you, it'll help you a great deal. Not only, you guys are still juniors, but if you read these chapters, you'll equip yourself very well for future Olympiads and team competitions and all the stuff. But I'm just going to tell you what are some of the things you can read over a period of time. Okay, and you don't have to read all the lessons, and just read whatever you can understand because you're still juniors. You can read the section has got numbers. I think prime numbers, factorization or whatever. And then you can read that section on, I've forgotten what I wrote there. There's a whole section on equations, something like equations, formulae or something like that. I'm not sure what it is. Equations, formulae. There's a whole chapter on that. They're very, very useful. You've got lots of formulae, the sum of the squares of the first natural numbers, sum of the cubes.
Sorry, Prof.
Yeah?
In your book, does it not state earlier on which chapters we must go through for the different SAMO rounds?
Oh, I see. Yeah. Maybe in the book itself, if you read, I can't remember. Did you read that? Yeah, if you read right at the beginning, I think I suggest to you, if you are doing junior, then you should read the certain chapters. And I tell you what chapters to read. Go and read right in the front, from the beginning, and see what you have to do to prepare yourself for round 3. I can't remember offhand, but I I can just tell you, you should do, what I can remember. I think we got grades 9, 10. This one. Oh, you guys are only grade. You're not even in grade 10, eh? Sorry, I assume that some of you are in grade 10. Okay, the geometry. There's this whole section on geometry there. That's a useful thing to have. And I don't know, man. There are some other things as well. It's taking too long to pick up the pages. Otherwise, I would, go into that. Oh, I seem to have lost the thing. Anyway, so those are the kinds of things that you can look at. And I'm sure there are others. There are lots of things about areas as well. Yeah, these are the lessons. All these are in the middle of the book, right? So I'm suggesting that you go and read the lessons, and that gives you a lot of information on the problems. So you can read it one time so that when you come to the problem, you'll get a lot of interesting things. See, the one important thing which you should do is similar triangles. When I come to you again, I'm going to talk about similar triangles. So I'm taking you into higher mathematics, which is grade 10, grade 11, and so on, because they do ask some questions even in round 3, which bear on those topics, but you need not know too much about it. With your intuition, you might be able to. So I'm going to tell you a few things about that. Okay. But as we go on, and if there's any theory that needs to be said, I will say it. And hopefully you will learn a few things. All right. Sorry, I exceeded my time again, but we haven't finished. I'm not sure. Yeah, we haven't finished the problem 11 or whatever. We still got a few more problems to do. I'll finish the thing off on Saturday, and that's the last time we meet. And we would have done 2 papers fully, and I might just do a few more problems from last year's. Okay, if we have time. Okay, guys, if there are any questions, okay, so we landed up with 27 people. I hope you learned a few things. I took it easy today. We didn't do many problems, but I hope you learned a few things. If you learned a few things, put your hands up. All right, so we got quite a few people who learned a few things, which is quite nice. Okay, so there are people, many people who have been in my class before who don't say much to me. You must speak. I'm glad to see Tato is one of the students I invited. He's here. And Ruwan, I think I heard you, Ruwan, a couple of times. Karen, yes, I heard you. But I haven't heard Jin Hon Ha. And Abigail, Celia, right? Christina, speak. Don't be afraid. Nobody knows who you are. They don't even know what you look like. So you don't have to be scared about saying some wrong thing. And nobody's going to laugh. No matter what you say, there is something which is useful. And Heinrich. My other little friend didn't come today, Andreas. He's usually got something to say.
Oh, no, he was here.
You are, yeah. Andreas, where are you?
No, I'm saying he was here. He left.
Oh, he's left. All right. Okay. Okay, then. Okay, guys, is there anything else that you want to ask me or whatever? I think you're right in about a week's time. So there's not much time left. But now it's during holidays. Take my book if you've got it and do many problems. You like problems. Take problems, try it yourself. And when you succeed in a problem, it gives you a great joy, you know. And take problems at level 3 and, you know, and when you're done with that, go to level 4 problems, try them out. If you're not done with it, look at the notes, whatever, learn a few things and go on, right? But You're on your own. Now you are young people. You're only in grade 8 and grade 9. When I was your age and in grade that, I didn't know 1/10 of things you guys know now. So I'm preparing you guys now for the future. I'm going to stop recording.